In this section, we're going to look at properties of logarithms. We're going to start off with the product property that says if you have log base b of a product, m times n, that's equal to the log base b of m plus the log base b of n. Or in other words, if you take the log of a product, it ends up being the sum of the logarithm of each individual factor. Let's first look at this with numbers. Consider over here the log of 15. We can write the log of 15 as the log of 3 times 5. According to this property, that should be equal to the log of 3 plus the log of 5. Let's verify that on the calculator. Pulling up your graphing calculator, if you punch the log of 3 times 5, you get the value of 1.176091259, or rounded 1.176. Now, let's punch the log of 3 plus the log of 5, which should give us the exact same value. And notice on the calculator that those two values are the exact same thing. So we're going to practice with the product property. If we take the log of 3x, notice we have the log of a product, 3 times x, so that should equal the log of 3 plus the log of x. Or if you have a product, let's say the natural log of 2 times b, according to the product property, that should equal the natural log of 2 plus the natural log of b. Now, the product property will work with more than two factors. Let's take, for example, the log of 3xy. Well, we said earlier that we know the log of 3x, so let's use the product property and say that that's going to be the log of 3x plus the log of y. Earlier, we said that the log of 3x is equal to the log of 3 plus the log of x. So if we just bring down our plus log of y, you'll notice that we can use it for more than two factors. Every factor is going to have its individual logarithm, no matter how many factors you have in that product. Let's work backwards. If we have log base 3 of w plus log base 3 of x plus log base 3 of y, and we are going to contract that or write that as a single logarithm where we can only write log base 3 once, the plus sign indicates that we used to have a product. So we'll have log base 3 of w times x times y. Or if we use the natural log of 2 plus the natural log of d, if we're contracting that back to a single logarithm, we have the natural logarithm of 2 times d. The plus in between, or taking the sum of those two logs, means that if we're contracting, we used to have a product. Now, one more time, if we have log of 6 plus log of f plus log of h, to contract back to a single log, we'll have the log of 6 times f times h. Now, let's throw another rule in there called the quotient rule. The quotient rule says if we have log base b of m divided by n, or log base b of a quotient, that will turn into the difference of the logs of the factors, or log base b of m minus log base b of n. Again, let's verify that on the calculator. Think of the log of 5, which could also be written as the log of 15 divided by 3. Pulling up our calculator, clearing out what we have in there from before. If we punch the log of 5 and get that value, it should be the same thing or we should get the same value as if we have the log of 15 minus the log of 3. So now let's pull that up on the calculator, taking the log of 15 and subtracting the log of 3. Notice that those values are going to be the same, rounded to 3 decimal places, 0.699. So now that we've verified that the property works, let's actually practice that with logarithms. If we have the natural log of x divided by y, which is a quotient, this property now says that we can take the natural log of x and subtract the natural log of y. Or if we have log base 6 of 3 divided by w, we can expand that into log base 6 of 3 minus log base 6 of w. Now we can put these two properties that we've learned together, the product and the quotient rule. Let's look at the log of 2a divided by 3b. You'll notice we have a product on 2 times a. We have a quotient because it's going to be divided by 3b. So if we use the quotient rule first, we'll have the log of 2a minus the log of 3b. But then we can go back and use the product rule. The log of 2a is going to be the log of 2 plus the log of a. The log of 3b is going to be the log of 3 plus the log of b. Now if we distribute the negative, we'll keep the log of 2 plus the log of a, distributing the negative minus the log of 3 minus the log of b. So we could have done this in one step if you'll think about the numerator and the denominator. The log of the numerator, or what's in the numerator, their logarithms are going to be positive. If the original numbers were in the denominator, or on the bottom of a fraction, we're going to counter that by subtracting the logs instead of adding the logs. Now, if you want to work backwards, if we're contracting to a single log, if we look at log base 7 of 4 plus log base 7 of f minus log base 7 of 5 minus log base 7 of g, and we're contracting back to a single log where we can only write log base 7 once, we know that the 4 would have to be on the top of a fraction because its log is positive. The f would also have to be on the top of the fraction because its log is positive. When we're looking at log base 7 of 5, the 5 is going to have to go on the bottom because of the negative in front of its logarithm. And log base 7 of g, the g is going to have to go on the bottom because its log was negative. So contracted back to a single log, we'll have log base 7 of 4f divided by 5g. Let's look at that again. If we have the natural log of 2 minus the natural log of 3 plus the natural log of m minus the natural log of p, and we're contracting or condensing back to a single natural log. The 2 has got to be on the top, its log is positive. The 3 would have to be on the bottom of a fraction because its log is negative. The m would have to be on the top of the fraction because its log is positive. And the p would need to go on the bottom of the fraction because its log is negative. They don't necessarily have to go in the same order, but if you'll remember, if the log is positive, it goes to the numerator of the fraction, and if the log is negative, its factor is going to go to the denominator of the fraction. One more example before we move on. If we have the log of 3 plus the log of a minus the log of 2 minus the log of b plus the log of c, and we're condensing back to a single logarithm. Again, the 3 is on the top of the fraction. The a, because of the positive in front of the log, would have to be on the top of the fraction. The 2, because of the negative, is going to go to the denominator of the fraction. The b, because the negative in front of the log, is going to go on the denominator of the fraction. And then the c would have to go back to the top because its log is positive. Now let's throw in one more rule called the power rule. The power rule says if we have log base b of m to an r power, that we can pull the exponent down in front of the logarithm and have r times log base b of m. I want you to think of the log of 9, which also can be written with the exponent, the log of 3 to the second power. According to this property, it says the exponent can be pulled down in front of the logarithm, or that should be the same as 2 times the log of 3. Again, let's verify that on our calculator. The first thing we want to do is punch in the log of 9. So if I punch in the log of 9, remembering to close my parentheses, getting that value, and then also punch in 2 times the log of 3, and look at that value, to the nearest thousandths place, those both values are going to be 0.954. So let's play with this property. Anytime we have the log of a number to a power, we can pull the power down in front of the logarithm. So log base 4 of y cubed is going to be the same thing as 3 times log base 4 of y. Or if we look at log of 3x squared z to the 4th, I'm going to use my product property first and say that I'm going to have the log of 3 plus the log of x squared plus the log of z to the 4th. Now I'll apply the power rule, and instead of the x squared, change that into 2 times the log of x. The log of 3, of course, would stay the same. And if we have the log of z to the 4th, I'm going to use the power rule on that individual part and have 4 times the log of z. Now, if we look at the next example, the log of the square root of x, you ask yourself, do I have a product, a quotient, or a power? Well, actually, we have a power rule, because remember, back from intermediate algebra, when you have the property a to the 1/2 power, or any time you have a to the 1 over n power, you really have a radical. And the index of the radical is going to be the denominator of the fraction. So a to the 1/nth power is the same as the nth root of a to the 1st. We can rewrite the log of the square root of x as the log of x to the 1/2 power. Now you can definitely see that we have an exponent, so we can pull the power down in front of the log and have 1/2 times the log of x. Now, if we have a nasty radical, I want you to think back to your elementary and intermediate algebra and clean the radical up before you try to apply any of the algebraic logarithmic properties. So if we have the log of the cube root of a to the 6th, b to the 7th, divided by c to the 8th, d to the 5th, I'm going to rewrite that as the log of a to the 6th, b to the 7th, divided by c to the 8th, d to the 5th, raised to the 1/3 power. Instead of the cube root, I'm going to take what's underneath the radical, or the radicand, and raise it to its exponential power. Now I'm going to clean up those exponents. So this really means we have the log of a to the 6th power raised to the 1/3, so 6 times 1/3 is 6 over 3, or 2. b raised to the 7th power, again raised to the 1/3, well 7 times 1/3 is going to be 7/3. c to the 8th raised to the 1/3, 8 times 1/3 is going to give me c to the 8/3. And d to the 5th raised to the 1/3 will give me d raised to the 5/3. Once I've cleaned up those radicals, now I'm going to use the college algebra properties of logarithms. I'm going to notice that I have product in there, I have quotient in there, and I have power. If we take this step by step and do product and quotient first, we'll have the log of a squared plus the log of b to the 7/3 minus, because it's on the bottom, the log of c to the 8/3 minus, because it's on the bottom, the log of d to the 5/3. So there's our product and our quotient properties. Now apply the new property of the power rule and pull each exponent down in front of its individual logarithm. So our final answer will be 2 times the log of a plus 7/3 times the log of b minus 8/3 times the log of c minus 5/3 times the log of d. Now, if we're going to contract back to a single logarithm, it will be easier to take this in a step-by-step fashion. First of all, take any numbers in front of the log and put them back up where they used to go as the powers. So 2 times log base 5 of x used to look like, before the power rule was applied, was log base 5 of x squared. Again, the power rule says the 3 used to be an exponent to the y, so we'll have log base 5 of y cubed. And the 7 used to be the power to the z, so minus log base 5 of z to the 7th. Now we're going to take one more step and apply our product and quotient rule. If we're contracting back to a single log, we'll have log base 5. The x squared will be on the numerator of the fraction. Because of the plus sign, the y cubed will be in the numerator of a fraction. Because of the minus sign, the z to the 7th is going to be on the denominator of the problem. Let's try that one more time, going a little bit more complex. This time you'll notice we have a parentheses, and in algebra we always work inside the parentheses first. So inside our parentheses we have the log of x minus the log of y. Well, that's the quotient rule. That says that it used to look like the log of x divided by y. And we're going to keep everything at this point the same. Now we're going to use the power rule and pull the front numbers back up as powers. So the 2 used to be an exponent to the x over y. The 3 used to be an exponent to the z. And the 1/3 used to be the exponent for the w. So that will tell me that I have the log of x divided by y squared plus the log of z to the 3rd minus the log of w to the 1/3 power. Now let's clean up this first one. The log of x divided by y raised to the 2nd power is the same thing as the log of x squared divided by y squared. Keeping everything else in your problem the same. Then we're going to use the product and the quotient property to contract back to a single logarithm. We have x squared y squared over y squared. The z cubed, notice that because its log is positive, it's going to go on the numerator of the fraction. The w to the 1/3, because its log is negative, is going to go on the denominator of the fraction. Now we can clean that up one more time if we'd like to, and write the log of x squared z cubed divided by y squared times the cube root of w.